Good morning. Today I am presenting our mini project titled XAI-MedLoc, an explainable deep learning framework for disease localization, chronic lung disease recognition system. Chronic lung diseases such as pneumonia, pulmonary edema, effusion, fibrosis, and pneumothorax are among the leading causes of global mobility and mortality. Early and accurate diagnosis is crucial. Yet in many healthcare environments, diagnosis still relies heavily on manual interpretation of chest X-ray images. Although chest X-rays are widely used because they are fast, low cost, and easily available, their interpretation requires expert radiologists, is time consuming, can vary significantly between individuals. With recent advancements in deep learning and convolutional neural network, automated analysis of medical images has become possible. However, one major limitation is existing AI systems is that function as black boxes, offering predictions without explaining the reasoning behind them. Our project addresses this gap by combining deep learning accuracy with explainable artificial intelligence, enabling not only disease prediction but also visualization justification of the model's decision. Problem statement. The key problems are identified. First, time-consuming diagnosis. Manual examination of chest X-rays can delay treatment, especially in high patient load environments. Second, subjective interpretation. Different radiologists may interpret the same image differently, leading to inconsistency. Third, multi-disease complexity. A single chest X-ray may show multiple lung abnormalities simultaneously. Fourth, lack of explainability. Most AI-based diagnosis systems do not provide visual or logical explanations, which reduces trust and adoption in clinical practice. Finally, resource constraints. Many hospitals lack experienced radiologists or advanced diagnostic support tools. The objective of our project is to develop an efficient, accurate, and explainable AI-based system that automatically detects multiple chronic diseases from chest X-rays, provides visual explanation to support clinical decision making. Scope of the project. The scope of the project includes development of an end-to-end deep learning system for chronic lung disease detection, use of ResNet for multi-label disease classification, integration of explainable AI techniques, mainly GradCam, CPU, GPU optimized training and interface. Target users: radiologists, medical professionals, hospitals, and healthcare institutions. Deliverables: a trained and evaluated deep learning model, disease probability scores, explainable visual outputs such as heat maps. Limitations: data set imbalance. For some disease, model generation may vary on unseen data. High computational requirements. Predictions require expert medical validation. Dataset and pre-processing. We use the NIH Chest X-ray 14 dataset, a publicly available dataset containing thousands of labeled chest X-ray images. Each image can be associated with multiple lung disease labels, making it a multi-label classification problem. Pre-processing stages. Images are resized to 224 x 224 pixels, converted to RGB format, normalized using ImageNet mean and standard deviation. Data augmentation techniques such as flipping and rotation are applied. These steps improve model robustness. Generalization. Methodology. Our system follows a structured pipeline. Data collection. Chest X-ray images and disease labels are collected from the dataset. Pre-processing. Images are cleaned, normalized, and augmented for consistency. Model development. We use ResNet 50 pre-trained on ImageNet. The final fully connected layer is replaced to support multi-layable output. Training. Binary cross entropy with logics ADAM optimizer is applied. Training is performed on GPU when available. Explainable AI integration. CAD-CAM generate heat maps highlighting disease-relevant regions. LIME provides localized region-based explanations. Interface. The system outputs disease probabilities. Visual explanations are generated for clinician in review. Next, architecture and design. The architecture begins with the chest X-ray image as input. The image flows through pre-processing layer, feature extraction using ResNet 50, multi-label classification head, explainability module. The final output includes disease predictions, confidence scores, visual explanation, heat maps. UML diagrams such as use case sequence diagram were used to model the system transactions and workflows. Algorithm used. We used algorithms such as ResNet 50. ResNet 50 is a deep convolutional neural network with 50 layers and residual connections. Key advantage: prevents vanishing gradient problem, learns deep hierarchical features, support transfer learning, enables detection for multi-disease simultaneously. This makes it suitable for complex image analysis. CAD-CAM. The CAD-CAM is an explainable AI technique that uses gradients to identify important regions, generates heat maps over chest X-rays, helps clinicians understand why a prediction was made. For example, in rural efficient cases, a CAD-CAM highlights affected lung disease. Implementation overview. The project is implemented using a Python and PyTorch. Key modules include train.py, model.py, XAI.utils.py. Train.py handles training loss, calculation, and model saving. Model.py defines the ResNet 50 architecture. XAI-utils.py implements CRAD, CAM, and LIME. The trained model outputs logics which are converted into probability scores using sigmoid activation. Explainability is applied during inference, not training, ensuring transparency without affecting the performance. Results and output. System outputs multi-label disease predictions, individual probability scores for each disease, CRAD, CAM, heat maps, LIME explanation overlays. Performance metrics: accuracy 90%, precision 93%, recall 92%. The system provides faster and more consistent predictions compared to manual analysis. Conclusion. In conclusion, our project demonstrates that ResNet 50 effectively detects chronic lung disease from chest X-rays. Explainable AI techniques significantly improve transparency and trust. The system supports faster, more reliable, and clinically relevant diagnosis. By combining deep learning performance with explainability, XAI-MedLoc bridges the gap between the AI and the real-world medical adoption. Future works. Future enhancements include integration patient clinical history and reports, deploying the system in real-time hospital environments, exploring advanced architectures and multi-model learning, improving explainability techniques for deeper clinical insights. Next, we can see about the implementation of the code and the output. Now I will briefly explain the implementation of a system, the execution flow of the code and the output demonstrated in the video, and then conclude the presentation. Implementation overview. The implementation of a project is done entirely in Python using the PyTorch deep learning framework. The system is modular and divided into three main components: model definition, training pipeline, explainable AI, and inference. The implementation begins by loading the trained ResNet 50 based model, which has been modified for multi-label lung disease classification. The pre-trained ResNet 50 model is imported from Torch vision and is fully connected layer is replaced to match the number of disease classes. This enables a model to predict multiple diseases simultaneously instead of a single output. Training and model execution. During training, as shown conceptually in the code, chest X-ray images are loaded using a custom dataset loader. Images are resized to 224 by 224 pixels, converted to tensors and normalized. Labels are prepared in a multi-hot encoded format. The training loop uses binary cross entropy with logic laws suitable for multi-class label problems. Adam optimizer for efficient convergence. The model is trained for multiple epochs and then saved as a .ph file. This trained model is later used during inference in the demo video. The use of CPU alteration when available significantly reduces training and prediction time. Explainable AI, GRAD, CAM and LIME. A key highlight of our implementation is the explainable AI model, which is demonstrated clearly in the video. Which when a chest XNet image is given as input, the model produces probability scores for each disease. CAD CAM is applied to the final convolutional layer. CAD CAM works by computing gradients of the predicted class, identifying the most influential regions in the image, creating a heat map overlay. In the output shown, warmer colors such as red and yellow indicate regions that strongly influenced the prediction. This helps clinicians visually verify whether the model is focusing on medically relevant lung areas. Additionally, LIME explanation segment the image into regions showing which parts support or oppose the prediction. Output demonstration. We can observe three major results. Multi-label disease prediction. The system predicts multiple lung diseases from a single X-ray image, each with a confidence score. Visual explanatory. CAD CAM. Heat maps clearly highlight affected lung regions, improving interpretability. Comprehensive diagnostic view. The output combines original X-ray disease probabilities, explainable visual overlays. This ensures the system does not act as a black box but a decision support tool for doctors. Final conclusion. To conclude, the project successfully demonstrates how deep learning and explainable AI can be combined to address the real-world medical challenges.